Hello and welcome back. I'm joined now by my second guest this morning, Martin Hart from TopLine.
Yes, good morning.
Good morning, great to see you, Marty. So we're here to talk today about some really cool new process
Yes.
that you have,
Yes.
that you've been working in collaboration with NASA, I believe.
Right, it's a new form of vibration damper
Okay.
to remove vibration out of boards, at least control it, attenuate it, in order to preserve the longevity of the board, not destroy itself when it's being excited through vibration through rockets or external concerns that would cause the board to start to actually vibrate and bend like a potato chip.
Right. So obviously these applications where they're going through high thermal excursions, or they're going down the hole or something like that.
Well, it's mostly excited through external vibrating motors, let's say fans,
Yeah.
loud noises, even loud noises. Like if you can imagine when you hear a big bass at high volume, your heart starts to actually
Starts to go, yeah.
So the same thing will happen with any materials, and a PC board is no exception. The board itself will start to vibrate and bend to a natural frequency of the board, and the whole idea is to attenuate that enough so that the components don't fly off the board and the board destruct in critical missions.
Okay. Yeah. So is there a bandwidth over which it operates? Does it go down to a certain
the technology is suitable for what's called random vibration and random noise. Let's say around 50 hertz up to 200 hertz, maybe even more. But it's for low frequency where the board actually starts to take on the natural frequency of the board caused by external excitation. And literally in our video you can see an example of two boards on a vibration table at the NASA lab, where the board in the background is unprotected without the vibration damping, which incidentally is called particle impact damper.
Right.
So the PID, the particle impact damper, as you can see
it. Yeah.
Yes. So the board in the foreground has the PID mounted right in the center of it, which is the correct place to place it. And you can see that the board protected is not moving as much as the unprotected board.
Yes, you can see that clearly.
Yes.
So the real heavy base, if you like, is where it creates the most movement, because that is omnipresent. It's not a directional sound so much; it's an omnipresent one. So that creates a real vibration.
It's not a predictable. It's like random.
Yeah.
So actually, you can see in the video too that the board is not moving consistently. Sometimes it slows down. Sometimes it bends extreme, and sometimes not. So it's a random noise situation.
So we're looking at it here, a little schematic of how it works.
Yes.
So it has some little balls in there.
Yes, there's design rules. This is an example that we've made out of a clear material so you can actually see. But inside the canister is tungsten balls. Tungsten was selected because it's the heaviest mineral or material available that is environmentally safe.
Right.
So tungsten's very heavy. You can pick that up. You can see for its size, it's quite heavy.
So here we have an example of it here.
Yes.
You can see, and this little capsule is filled with the tungsten balls.
Yes.
And it does feel quite heavy.
Yes. Yes.
So
this little canister is designed to protect a board that might weigh 1.5 kilograms, maybe 2 pounds.
Yep.
So it's quite a sizable board with all the components. The design rule of the PID is fairly simple. It's a very simple device. The weight of the PID should be 10% of the weight of the entire assembly.
Okay.
So once an engineer knows what the assembly will weigh, then it's a simple matter of using our formulas to look to see that particular height or width to have room available to mount it onto a board.
Okay. So you change the size of the the PID depending on the size of the board.
Yes, that's very important. So the PID would be 10% of the mass of the entire board.
Okay.
The second design rule is quite simple too, and that is you mount it either in the geographical center of the board or the place on the board that's vibrating the most. So some boards are vibrating more at the end because it's laid out in a way where there's other components on the board that are heavier,
right.
Or there's sometimes the board is unsupported at an end if it's plugging in it to a connector.
Right.
So those are the two main design rules. Internally, there is a 10% headroom, so the canister is filled to 90% capacity. Now, the secret sauce here is that the tungsten balls will actually escape gravity.
Right.
So that's when there's no vibration, the tungsten balls are stationary. But when the board flexes at a certain rate, it actually will start shooting the balls inside of the housing up to hit the ceiling.
I see.
And while it's hitting the ceiling, it's pulling the board back into position.
So it's acting a little bit like a dynamic board support, which makes me wonder if they know the board is going into that sort of environment, why are they not putting more standoffs in there to act as board support?
Well, that's traditionally the three ways that engineering has dampened boards. The traditional way is either to make the board thicker. So often on mill designs, mill spec designs, you'll see the board being 2.5 millimeters thick or 0.1 inches as a minimum, and that was not a nice to have, but that was because the board will vibrate, and bend a little less as it's thicker. So that, of course, adds weight and complexity to have a thicker board. The second way traditionally has been to put a framework around the board.
Yeah.
And the third way is to have little rubber bumper cushions. So all of those have been used for many, many years in the past. This is a novel method that NASA came up with.
Right.
And they filed a patent, they have the patent, then they licensed and sold it to TopLine.
Okay, good. I mean, does it have, because it's emanating a dampening type of effect?
Yes.
Is it creating less stress than, say, something that is rigidly supported?
Well, the result is we don't want the board to bend to a point where the components are coming loose.
No.
So this is a dampening effect. It's simplistic in that no metal framework is required. It's finding let's say the best place on the board to place it, which is typically in the center or in another place where you can actually see a board move, so you know where to place the...
So how do you attach it? Do you glue it?
Okay, this is attachable several ways. One is to use epoxy. So there's actually a flange on the bottom of this that will get epoxied onto the board after the components are assembled. The other way is there's a surface mount attachment, so it can go through reflow without the canister, just the flange itself.
Okay.
So there's threads on the flange. So after mounting, then you screw it on, and there's a pin to lock it so it doesn't unscrew itself through vibration.
Excellent. Well, it's a really novel idea,
Yes.
Martin. I don't know where you keep finding these things. I mean, every time I see you, you have some really cool new technology. So
Yes.
thank you for sharing that with us.
You're welcome.
I appreciate it. And thank you for joining us today.
All right, very good.
We're going to cut to a commercial break now. And after that, we'll be finishing up from our presentation here at Apex.
Okay, thank you.
Okay?
Okay.
Thank you very much. It was
All right.
very good.